Always feel like I come into Zoom and they move the recording button to a different location every time I come. Uh, Welcome everybody to the March meeting of Tucson Amateur Astronomy's Fundamentals Group. For those, I think most of everyone here is a returning person, so that's what I can tell. But for those who are watching this after, um, this group meets every second Thursday of the month, and we typically give two presentations that vary. One of them varies between an astronomer and a constellation, just to give some general interesting background knowledge on things in the night sky, while the other is a slightly more in-depth presentation on topics of a wide variety of that astronomers would likely to be find interesting. So tonight, keeping with that theme, the constellation that I will be presenting is Aquila, and then following that with a little bit more of a high-level overview slash dive of the Event Horizon Telescope. So getting started with Aquila, and turn on my pen here. So Aquila is a northern constellation in the night sky. It is also the 22nd largest constellation out of 88 overall. And I do apologize if it's going to sound like I'm reading slides a lot tonight. One of these presentations I did quite a while ago, and the other one was more of a last minute put together. So I'm not rehearsed on these as I normally would be. It is the Aquila is one of the constellations that was originally cataloged by Ptolemy, but like many of the constellations that Ptolemy did present to us, they did have much earlier roots from other civilizations that the Greeks interacted with, most notably the Babylonians. This constellation is part of what's known as the Summer Triangle and makes it relatively visible in the early evening, relatively early from June through November, although it is currently rising in the night sky right now at around 3 a.m. From northern latitudes, it is a constellation that is visible for a significant portion of the year because of its location on the in the night sky plane. From our perspective, this contains a small number of objects that we'll find interesting. It contains 13 open clusters, two globular clusters, and two galaxies that are brighter than 13th magnitude. Most of this is because the Aquila itself lies somewhat close to the galactic plane, being relatively close to Cygnus. Some interesting portions of this constellation that um, include that a nova was first cataloged in Aquila in 1980, which was cataloged by a Polish surgeon. At the time, this was the brightest nova that had been observed since the invention of the telescope, reaching apparent magnitude of negative 0.5, which is brighter than the star Vega, although nowhere near as bright as the brightest star of the night sky, Sirius. Interestingly enough, one of the largest known galaxy filaments in the observable universe, which is known as the Hercules Corona Borealis Great Ball, extends through Aquila. So, being its name, it is a large gravitationally bound object of galaxies that goes not just through Aquila, but Hercules and Corona Borealis as well, which are nearby. This gigantic string of galaxies has a general length slash of about 10 billion light years, which seems like an odd measure. I'm not quite sure what the overall volume of this region of space is. Look, I didn't really find any information to back that up in terms of or to supplement that. So it's kind of a weird measure for this. Uh, Also of interest is that the space probe Pioneer 11 is eventually expected to pass through the star system Lambda Aquilae at about 4 million years. So I don't think we'll be around to go and sit there and watch for that, especially I think the probe has been without power for many decades at this point. This is a star chart showing both the constellation and the surrounding region. So we have Aquila being surrounded by Eculus, Delphinius, Hercules, uh, and I think Cygnus is over here, where over here to the lower left. Uh, so the constellation itself, as I did mention, does predate the Greeks by some time. It actually does apparently have some ties to ancient Egyptians mythologies before it eventually made its way over into Babylonian Mesopotamian mythologies. Specifically, the Egyptian mythos associated the constellation with the falcon-headed god Horus, who was the Egyptian god for kingship, the sun, and the sky. Uh, Mostly just part of his appearance. He does have a very interesting and humorous story about how he and his brother Set defeated his brother Set to become the first king of Egypt. But some of that included some inappropriate material for this. So I'll leave that to for you to research that on your own. It is quite humorous, depending on who you want to read that tells it. The Chinese also have some origins on this, telling the story of Qi. I'm going to butcher that name, and I apologize. And his two children, which were represented by three other stars in Aquila, who were separated from Xi's wife, Ji Nu, who was represented by the star of Vega, and telling which is on the opposite side of the galactic disk. And so in this telling, the Milky Way is itself acting as the Great River. The Greeks associate a constellation with an eagle named Atos Dios, who was basically Zeus's overglorified carrier pigeon who carried around his thunderbolts and did other things with Zeus. At one point during the story that elevated him to constellationhood, he ordered Atos to go and fetch the Trojan prince Ganymede, whom Zeus wanted as a cupbearer, which was kind of, if you remember some of the old satirical Roman films from the 70s, where there's that one guy with the fan dropping grapes in the emperor's mouth while the emperor just relaxed on his throne. That was sort of the role of the cupbearer. And Ganymede was known as being, at least in the Greeks, a very uh, handsome and beautiful man. And so Zeus was like, "Yeah, I'm the king of the gods. I deserve to be surrounded by people who, you know, are held up to great stature." And so he's like, "You know what? You're gonna come serve me." And uh, so Aquila basically kidnaps Ganymede and takes him over to Zeus on Mount Olympus, where the pair enter a relationship. It's kind of conflicting on some of the sources I saw whether this relationship was platonic or romantic in nature. Moving on into some of the notable objects in this constellation. So this is a just a general rough listing of some of the stars, clusters, and galaxies that are available in this region. Uh, Despite being close to the galactic plane, there's not a lot of very large extended, there's actually almost no large extended objects that are visible to us in terms of clusters or galaxies, unfortunately, which makes it does kind of look for a little bit of boring observing if you're into deep sky objects overall. The primary star in this constellation is Altair, which derives from the Arabic phrase meaning the flying eagle, again, keeping with the eagle theme of the constellation itself. It is an A7V main sequence star. So this is similar in type and classification to Sirius, which itself is also an A class main sequence star. It has a visual magnitude of about 0.76 and is roughly both in mass and radius 2 times that of the sun, but is about 11 times more luminous and is somewhat close at about 16 light years distant. This car is itself rotating very quickly, which but it is actually rotating so fast that it is close to the point of where its own rotation would tear the star apart. It wouldn't have the gravity of the star itself wouldn't allow it to hold on to the hydrogen of its shell, and so the star would just rip itself into pieces. Unlike, to give you kind of comparison of how quickly the star is rotating, the sun itself rotates about once every 25 days, whereas Aquila completes one whole rotation every 8 hours. So even though it's twice the size of the sun, it's completing that rotation very, very quickly, even faster than Jupiter. Jupiter is like a 12-hour day. So this is very huge, very fast spinning object for a star. Showing the position here on the left of the star within the constellation. It is the brightest star in the night sky. Will be certainly the easiest one to recognize, especially for those who are familiar with the overall northern triangle asterism, which is a very large asterism consisting of the stars Deneb, Vega, and Altair. I wanted to say Aquila for some reason. I don't know why. And on the right is a rough as a positioning of where Aquila fits on the Hertzsprung-Russell diagram. So it is, as Claire mentioned, it is an A-class main sequence star, so it does have a whitish appearance. On to some slightly more interesting stars is Eta Aquilae. This is a multi-star system with two confirmed components, and there is a suspected third, but it hasn't been fully confirmed, or at least from the resources I saw. It might be a little bit more apparent from Gaia data, but I don't have the expertise to go through that. This star is a much cooler F6-1 supergiant. It is a Cepheid variable star, so it is one of those stars that does help serve as a measure on the overall cosmic distance ladder. Being a Cepheid variable, it does have a change in brightness over time with a shift between magnitude 3.87 and magnitude 4.3. So very small overall change. This brightness period lasts about every 7 days. It is, being a supergiant, very large in terms of radius of luminosity, coming in at around 59, almost 60 times the radius of the sun, and 3,400 times the brightness of the sun itself, but only at about 4 times the mass as fitting of a supergiant. Claim to fame for this is that the person who discovered the galaxy Messier 64, which I think is the Black Eye galaxy off the top of my head. It's one of the two named galaxies that are fairly good imaging targets. Edward Pigott, who discovered that object and just sent it over to Messier for inclusion in his catalog at some point, was also the first to catalog it as the star as a variable in 1784. So this fits closer to the talons, I believe. So over here is the head, and here are the two wings of the keel. So this is, I think, closer to where his talons would be if the bird was setting. And then it fitting on the supergiants, it is very much way off of here in the Hertzsprung diagram, way off on the side. V Aquilae is a carbon star, and being carbon stars, they're all somewhat variable in nature. So just by definition of being a carbon star, this star is classified actually in a special carbon star scale called the C scale. I think I've touched on in other topics, but it's classified as a C5 with a visual magnitude that stretches just slightly outside of visual range at 6.6 to 8.4. Making it one of those targets that would be an interesting binocular target for a carbon star. That's because carbon stars are all that deeply red, and generally you can see the redness of carbon stars without much trouble. The star being a Cepheid variable is very large and diffuse, noted by its radius of about 234 sols, but a mass of about 2.5 itself. 2.5 sols. So this object was first discovered by George Knott in 1871. That period varies between it being a semi-regular variable. It doesn't have a single fixed period of variation, and so that varies between cycles that can last anywhere from 400 to 2,200 days. And I do not have a star chart or information of that just because the resources that I used to pull those did not include that in the database. So deep sky objects. As I did mention, despite its proximity to the galactic plane, as this rendering of some of the data shows with the galactic plane passing right through the constellation here over into the right-hand side of the image, it does lack a lot of very large extended deep sky objects, although there are potentially some dark nebula interesting imaging regions like over here off to the side for Aquila. This does make it a little bit more challenging just trying to observe individual objects within the galaxy, mostly because those would be open clusters and globular clusters. And given its proximity, you're looking through a lot of amount of star field anyway. So for many open clusters, they would be challenging to observe because, as you'll see, I think I have one of them in here. They're very small and very, I don't want to say diffuse is the right term, spread out. But I think before we get to that, we do have one galaxy that's worth mentioning in here. This is a face-on spiral galaxy and a Seyfert galaxy. So Seyfert galaxies are, to a certain extent, active galactic nuclei galaxies. The more prominent example you may be familiar with is the Seyfert galaxy Centaurus A, which does is starting to actually get into good positions here in the night sky for those who like to look over in that region for some Omega Centauri, excuse me, got that name backwards. This galaxy is a magnitude 11.2 with being a very small size, about 3 arc minutes. So it is a galaxy that you would need at least 8 in optics to get enough magnification and aperture to be able to pull this out. It is the brightest of the galaxies that's visible in Aquila, so that can give you an idea of where your challenging targets for if you're looking for things here in this constellation to go observe. It is 74 million light years away, and it has a diameter of about 85,000 light years, making it slightly smaller than the Milky Way as a whole. This is a visual magnitude, not a framing check showing how the galaxy would appear with a 10 millimeter eyepiece on a 8-inch Schmidt Cassegrain. So to give you kind of a rough idea of what you might need to observe this galaxy, it is, as you can clearly see, a very small galaxy overall, considering that this is like 200 times 200 times magnification, and it's still basically about the size of I think this is the same size as the Ring Nebula itself, so it is a very small galaxy from our perspective. We have then the globular cluster NGC 6760, which is the densest, apparently from our perspective, the densest globular cluster within Aquila. It is a apparent magnitude 9, with an apparent size of about 5 arc minutes. So it is a very small, from our perspective, globular cluster, unlike some of the more impressive globular clusters nearby, like Messier 13 over in Hercules. It has about 3,500 solar masses contained within the small contact object, and being a globular cluster is about 24,000 light years away. So still a big galactic neighborhood. Again, this is a 10 millimeter eyepiece on an 8-inch Schmidt Cassegrain to give you a rough idea. We can see that it does have a very dense core, so it should be something that would stand out against the star background, but expected to look more like a little puffball of stars without if you do go hunting for it, without even with large optics. This is a visual image, not a visual image. This is an image taken by an individual, which I found on Astrobin. This was done using a 1800 millimeter focal length telescope, just try to give you a better idea of the overall star field and how to pull out this object with it being this very dense core with a very extended background field of stars. And I actually did not include any open clusters like I thought I did, because as I did mention, they were challenged for me to point out on a start on the images that I was able to acquire. So it's very hard to unlike some other more prominent open clusters to be able to distinguish like, hey, am I actually on the open cluster or not? So I left those out. I do apologize for them misleading there. Questions or comments on Aquila before I move on? Okay. So on to the main topic for today, which actually was what I actually had a lot of fun researching on, although I am not at all going to be able to do this topic justice in terms of content. There was just a lot to unpack here. And for time, I am going to kind of skip over a lot of the more interesting details just because I was running short on time putting this together. So in this, we're going to talk a little bit about what the goals of the Event Horizon project were, uh, and highlight three individuals in the leadership hierarchy of the telescope who were responsible for both coordinating, organizing, and establishing the project as a whole. We'll give a brief overview on the individual observatories that make up the array, just highlighting at a very rough detail where these telescopes are, what they particularly bring to the table, what their size is, that sort of information. We're only be going over the 8 original elements of the array. That array has since been extended to include 3 other radio telescopes, but for the sake of time, and those slides are repetitive, I'm not going to go into those. And we'll give a little bit information on interferometry, which is the key technique that enabled the success of this project, and we'll wrap it up with showing some of the other discoveries that were made with the Event Horizon Telescope after their famous pictures of the supermassive black holes Sagittarius A star and the M87 star. So the impetus for the Event Horizon Telescope definitely hinges on astronomers' fascination with black holes and the recognition that they know that general relativity itself is somewhat incomplete. There are things that it can't explain concisely, such as dark matter. And there are many hypotheses tried to say, like, well, where else does general relativity break down? Does it potentially break down in these extreme gravitational environments around a black hole? What can we use to give us more information that may help us point in a new direction for reconciling things like dark matter and dark energy. The other key thing here is that with black holes is that we're limited in terms of what we can actually do with these objects. They are all generally very small from our perspective, and being by definition, they're just generally very hard to detect. So until gravitational wave astronomy, we only had indirect confirmations of their existence in the forms of things like large jet structures, high energy gamma ray X-ray sources, gravitational events that we're all like, hey, these are indirect pieces of evidence that overall build into pictures that yes, these things must exist, but not any like direct, hey, we can go photograph you like we can with a nebula and say, yes, this thing exists. So this is rather going from having a whole bunch of very strong indirect evidence of their existence. They wanted to build up yes, these things actually exist with more direct observations. And given the extreme environment around black holes, was hoped that observations within this would, as I did mention, give more information about where we could pursue things for physics itself with various models and theories. Some other interesting things that this project itself also wanted to answer are things like, why is it that in our galaxy, the supermassive black hole Sagittarius A star is so dim compared to other supermassive black holes? Uh, since it is a difficult target to see through because it's through so much gas and dust to get to the center of our galaxy. Um, you know, Imaging this environment still is primarily done through pure radio astronomy in the first place. But we don't really definitively know like what sort of mechanics led it to having, not having active jets. Is this just a phase of where the supermassive black hole galaxy is today? Was there some other reason that it doesn't have, an active accretion disk or jets or those sorts of features? Another, it also wanted to answer, we say that with a black hole it has an accretion disk in some cases, and this glows because the material itself, as it approaches that black hole, is heated up by friction. But the question becomes, is what causes that friction? Uh, with the accretion disk, which themselves are generally, actually surprisingly, I didn't know this, was very diffuse themselves, and so the matter within the accretion disk doesn't actually interact with itself. So it's not friction of the molecules being sped up interacting with each other to produce the glow. It's other processes, and so they wanted to get a better handling on exactly what those processes were. And they also wanted to give a better idea on what mechanisms give rise to black hole jets. The issue with all trying to accomplish these is that, as I did mention, black holes themselves are very hard to observe. We had only ever really observed them through indirect measures beforehand. Things like X-ray, gamma ray observatories, relativist jets, or other influences. At least until the advent of gravitational wave astronomy, which had just published some of their first results while EHT was collecting their data for the M87 and Sagittarius A star supermassive black holes. So the other thing, being these very general stellar mass black holes are very small objects, and you can't also image black holes unless they are actively interacting with material around them. Otherwise, they're just inert. You can't really see them at all. They're not emitting X-rays or gamma rays or other material or other signals that we can reasonably detect, because X-ray and gamma rays come in part from the interaction of material in the accretion disk. So that limits the number of candidates that this project could actually look at. It couldn't be a stellar mass black hole because they are incredibly small, and they needed to have an accretion disk. So to give an example of just how small they are, if you took the sun and turned it into a black hole, that object would have a diameter smaller than most neutron stars. The sun would essentially go from a 1.4 million diameter object to a 6 kilometer diameter object, which is like if you took that star and planted it over Tucson, it would probably fit mostly over the general central area of Tucson itself. On the other side of that, we go into the supermassive black holes, and those have very wide variations in mass from the millions to billions range. But even if you were to look at Sagittarius A star, which is the closest supermassive black hole to us, which it has a diameter of 24 million kilometers compared to the sun's 1.4 billion kilometers. So Sagittarius A star would still, the event horizon of that black hole would still fit within the orbit of Mercury. So given its distance and its size, imaging Sagittarius A star is equivalent to imaging a piece of fruit on the moon from Earth. So to kind of give you an idea of the angular resolution here involved. So these challenges completely rule out the ability for this object for the Event Horizon Telescope to image stellar mass black holes, because they're very small, and even and at their distances would be smaller than any pixel we can currently measure with. So this is an example here of all of black hole mergers that have been detected to date by the Legal Observatory as of August. This was primarily here just to harp on the fact that, even though we have all these, we've seen all these observations with LIGO and Virgo, nearly all of these black hole mergers occurred outside of our galaxy. And so even though there's a great abundance of solar mass black holes, it's just not feasible for us to go after them with the techniques that EHT leverages. It is very much one of those, it's very much a telescope geared towards supermassive black holes. But to start this project, we have to talk about three people. The first is Shepard Dolman. He is the individual who actually organized and created the EHT collaboration as a whole. He currently serves as the director for the collaboration, and he is attached to Harvard University. He earned his PhD from MIT in 1995 under Bernard F. Burke, who is notable for being the co-discoverer of the first Einstein ring. I apologize for the typo there. For those who are familiar, if you have seen pictures of galaxies being warped into this weird circular distortion, from those are Einstein rings, which are used as essentially gravitational lenses. His main research focus, Bernard Dolman's range research focus, is challenging problems that require ultra high resolution. And he did his PhD thesis on imaging active galactic nuclei with 3 mm very long baseline interferometry, which is what that acronym stands for. And if you can actually read this PhD thesis online. It is 120 pages, and you can find it directly from the Wikipedia link for him. But you can immediately see just from the abstract of it that there's a lot of similarities here with what would eventually go on to be done with the Event Horizon Telescope. So he almost set himself up to lead this collaboration, and he took it on. Our next key figure is Heino Falke. He currently serves as the chairman of the board of the EHT Science Council. Which I'm not quite sure what their overall roles and responsibilities are. I think it's more of managing the technology aspects of the project as a whole. He is attached to the Radboud University, and I will not Nimjeg. I can't pronounce that for that last word. I apologize. Which is based out of the Netherlands. Curiously, he did briefly work at the University of Arizona in 1999 before moving on to other projects. He himself is primarily a theorist, although he does do occasional things with and the experimental aspects. And right now, from what I was able to gather, he is engaged in studies of how to get a radio telescope onto the moon, just to kind of escape a lot of, the typical things of like, hey, yeah, Earth has an atmosphere, and so there's things we can't do with it because it has an atmosphere, but we kind of need the atmosphere to live. Oh, well. Curiously, he is the originator of the term black hole shadow, which I'll briefly talk about, but I'm not going to be able to adequately describe just because the resources I found to actually say to say what it is are somewhat lacking. But nonetheless, he is an originator of that term, which was one of the cool things that you were able to see in the first two images that the EHT collaboration produced. He was also a key figure in establishing the LOFAR radio telescope array, which uses interferometry, which is the same technique roughly that the EHT uses in order to image things, although it was essentially a much smaller scale version of that telescope, where instead of globally distributed radio arrays, they were just a bunch of radio arrays distributed mostly throughout Europe. So this gave him a good experience to bring into the EHT collaboration to help manage the aspects with coordinating and establishing these very distant radio observatories into the single unified unit. And then lastly, we have Anton Zenith, who is the chair of the EHT collaboration board currently. He is primarily responsible for making many of the technology, or his research group was made many of the advances in interferometry that helps contribute overall to making to enabling the observations that EHT would eventually go make. He is primarily interested in extragalactic radio sources and active galactic nuclei, and is attached to the Max Planck Institute. So with those people out of the way, trying to highlight some of those.
Into the glass to produce several solid cylinders. The drill cuts that larger and thicker than the fire.
Sorry about that. We go talk about exactly what the capabilities of the EHT telescope were. This originally the telescope was comprised of 8 individual sites as of 2017, although, as I mentioned, it did expand to include 3 more observatories by 2020. There were also 2 other observatories that were originally included in the array, but they were retired over the course of this period, and so no longer active. But there's still, to date, there is 11 elements in the array. The main thing that most of the public knows about from this particular collaboration is the 2 images that were announced of the supermassive black holes M87 star and Sagittarius A star, which it was, I'll quote unquote, imaged at 1.3 millimeter wavelengths, which we'll talk about briefly here in a second why that was the case. The array itself is able to achieve a diffraction limited resolution of 25 micro arc seconds. Diffraction limited resolution means that the telescope itself is limited not by things such as atmospherics or other physical aberrations, but simply pure physics, the ability to capture light at this scale. A little bit more nuanced than that, but you could roughly just think of meanings like they can't get better than this with the telescope that they with the technology they currently have. The diffraction limit is the absolute best you could do on a telescope. The amount of resolution within one single pixel of an image on the EHT is 4,000 times greater than a single pixel on the James Webb Space Telescope, which has a resolution of about 0.1 arc seconds on its highest magnification instrument. To put that into perspective, about how if you were to sort of tune EHT to, if you were to make a super compact EHT to look at as a normal telescope, a person in Paris, France, there's a typo there, I apologize, can, if they were to use it as like an optical telescope, they could essentially read a printed newspaper from somebody in New York City at the same time, and with perfect clarity. The additional 3 observatories that were added since 2018 have also allowed it to expand its capabilities somewhat, pushing its resolution down to 19 micro arc seconds. So with those capabilities, though, you have to ask the question is, well, how are they able to accomplish this? And exactly what allows them to do this in the first place, which leads us into 2 very interesting topics called interferometry and aperture synthesis. So interferometry is to give you a rough idea, this isn't a perfect analogy, but it'll have to do, is you imagine when you throw 2 rocks into a pond, they'll make concentric waves out from their point of impact as they radiate out from these central points. And at some point, the waves from these 2 rocks will meet with each other and interact. And depending on where along this track of where these 2 wave patterns meet, sometimes those waves will merge and become a bigger wave. Other times they will collapse and dissipate an individual wave element altogether. And so interferometry is looking at how these waves collapse and enhance each other, and they use this to work backwards to reconstruct more information about what emitted the waves in the first place. So it's like looking at the waves in order to define information about the rock that caused them. There's a lot of math involved with that, but that's kind of the rough gist about kind of what's going on here is they're looking at how the different radio waves interact with each other at the same time when they're emitted from the same source. Although in the case of my analogy here, I'm using two rocks, whereas in interferometry, they're only looking at one source. In this case, a single galaxy or a black hole, rather than two sources. This enables what's known as aperture synthesis, which allows them to use this feature of interferometry to virtually create a telescope that is physically larger than any of the individual elements of the telescope array itself, which is a mouthful to say. But to understand that, we need to understand what a baseline is. So a baseline is the separation between two individual elements of an interferometer, which is, in our case, two individual elements of the EHT radio telescope array from a signal's source. So in this case, our signal source is a black hole. So it's just how far, if you were to draw a triangle between the black hole and two elements of the array, what is the distance between those two elements at the far end of the triangle? And that distance is the baseline. However, the Earth is round. It rotates. So even though from our perspective, at our physical location, any two elements are in a fixed position to each other, the rotation of the Earth, because you're looking at this from the source's point of view, the angle and distance between those two elements changes. And so even though these two sources are fixed, their baseline distances change as the Earth rotates. So this becomes important is because we look at all of these different baselines in order to combine them in very specific ways, which allow us to create this super telescope whose aperture is essentially the longest baseline between two elements. And that's how big your quote unquote aperture is. So there's a lot of math involved, which means that in the case of EHT, the two farthest elements allow it to create a telescope whose aperture is the same size as that of the Earth itself, just because of where these telescopes are positioned. Now, your next question is, well, why do we need so many telescopes then? Why can't we just say, well, let's put what telescope A on one straight line distance on the Earth, like say at the North Pole, and put telescope B in the South Pole, and we don't need all these other elements. But interferometry doesn't work like that. Showing here in these images about how interferometry, when you try to decompose the signals that it gets, if you just took those two elements and you had them you essentially have a straight line. And so if you just do that, you're not really capturing any significant detail. It looks like a garbled image. There's not a lot you can tell. So you need a lot more elements in the array in order to recover information about the object you're observing. So as we can see here, we have this horizontal line and a vertical line, and they're really just still distorted images. But if you start doing it to more complex geometric patterns, you can clearly see a much more defined features of the image and the object you're trying to imagine. But the distance itself also matters between these objects, not just the arrangement. So as you start spacing these elements and spacing them farther and farther out, you can get more information about the signal, although it is possible to start spacing things so far apart that you are oversampling your images, and instead of getting, you go from like a hyper signal to noise ratio, which makes certain things harder to tease out, and you start getting, from noise to really good signal to noise ratio, back to like a weird combination of signal to noise. So it isn't just a matter of, it's a combination of having telescopes that are geometrically good and positioned, how far they're positioned, and what the arrangement actually is that contributes overall to the capabilities. It's not just as a matter of, we only need two telescopes. Each of the individual element is responsible for breaking something that's able and producing these images. Now, one of the questions that I've actually seen quite often when people ask, when talking about this is, why can't we use this same technique in infrared and visible light astronomy? And we actually do. There are there is actually an optical and an infrared interferometry array, but the distinction here is that even though these exist, we can't use them on the same scale that we can with the EHT array. This is because in order to do this, we have to make very precise measurements of the amplitude or the light intensity and the frequency or phase of a signal. With radio, this is incredibly easy to do. We've been doing it for many years, and we've been able to use interferometry itself since the 1950s. However, because of the much shorter wavelengths of visible and infrared light compared to radio waves, this challenge is extremely complicated. And we've only been able to have the technology to do this since the late 1990s. And unlike radio waves where you could just record this signal and look at it after the fact, you can't do that with visual and infrared. You actually have to pass it through a series of, lenses, arrays, and other optical elements in order to extract this information about the phase and the amplitude. But you have to pass the signal from, all of your sources that are in the interferometry array at the same time. Because going back to the waves, instead of recording the waves and looking at the waves afterwards, we actually have to record the waves as they're interacting with each other, which means that it's really hard to try to do this because you can't basically build a laser beam of a telescope from 1,600 miles away because there's just not enough light signal to go down this route. So this limits visible and infrared interferometries to very small scales and not anything that we could reasonably do over the large geographic distances that we can with radio waves. So this is a positioning of all the individual elements of the EHT array. There's actually a typo here. Whoever made this infographic, now that I see that, because Kit Peak is on the other side of the SMT telescope geographically, so I don't know why they did that. But the blue dots on this image are actually the positions of the telescope arrays that were added to EHT after 2018, while the orange ones are all elements of the original array. So one of the but because of the nature of what they're doing with the EHT, you can't add any any arbitrary radio antenna dish into this array and expect it to capture the information. Individual radio waves are sensitive to very specific frequency ranges, and in order to capture the images of a black hole, these radio antennas have to be capable of analyzing and receiving signals in the range of 220 to 350 gigahertz. To put that frequency range into perspective, the frequency range used for your cell phone radio is 5 gigahertz. So these are very, very high frequency, very long wavelength radio sources. So this frequency range puts these telescopes in an area of what's known as sub-millimeter astronomy, which sits between the far infrared and the microwave regions of the electromagnetic spectrum. To compare that, James Webb itself was only good up to the mid-infrared region of the spectrum, and so this is well beyond what James Webb would be able to see. This frequency range is actually very important overall in modern radio astronomy because half of all radiation emitted by stars, galaxies, and other objects is absorbed by gas and dust and then re-emitted in the far infrared and sub-millimeter ranges. So this is a huge amount of data that tells us things about various objects in the universe, why there's so many of these arrays. However, because of the frequency ranges in which these telescopes observe, they are constrained by the Earth's atmosphere. These frequency ranges are very highly absorbed by water, and so these observers need to be placed in very dry locations and at very high altitude, just generally, in order to mitigate the effects of water and humidity on the telescopes. But because these are not optical telescopes, these are able to observe at all hours of the day at all times of the year, as long as the water and humidity conditions at the observatory permit, which is important for one particular telescope in the array, which is here, which are here in Arizona. Running through the list of telescopes in this array, we'll start with the sub-millimeter telescope, which is here in southern Arizona over by Mount Graham. Well, on Mount Graham. This is operated by the University of Arizona, and we won't talk about the other element, which is Unkitt Peak, which they added in 2018. But this telescope uses a 10 millimeter antenna, and it observes within the 205 to the 490 gigahertz range, which places its wavelength range of underneath 2 millimeters. Remember how back when I led off with this, that with the EHT images for M87 and Sagittarius A star were in the 1.3 millimeter range for wavelength. Now, for those, since being here in Arizona, it is not perfectly dry all year round. And so this telescope does shut down during the monsoon season, unlike most of the other telescopes in this array, which generally operate year round. From there, our next telescope on this list is the Atacama Pathfinder experiment, known as APEX. This is one of several telescopes that's located in Atacama, Chile. This observatory is operated by the Max Planck Institute for Radio Astronomy and uses a slightly larger 12 millimeter antenna, but it does have a very different frequency range compared to the SMT, going from 200 gigahertz to 1.2 terahertz in its overall frequency range. Interestingly, this is a telescope that served as a pathfinder or prototype antenna for what it would eventually go on to become the ALMA array, which we'll talk about here briefly in a second. Pathfinder experiments are basically technology demonstrations to prove, like, in order to suss out components of larger, more complex instruments before they, throw a whole bunch of money at a multi-billion-dollar instrument and say, oh, well, we found out we couldn't build this. So these are incremental steps to building more complicated objects. On the other side of the planet, we have the IRAM 30-meter telescope. This is one of the larger single elements in the array, which is based on the Sierra Nevada mountains in Spain. I didn't know there's two Sierra Nevada ranges, the other one being here in the US over in California. So that was a little bit interesting to me. This is located on the southern tip of Spain, close to the Mediterranean coast, is where this is geographically. It is operated by the Institute for Radio Astronomy in the millimeter range, which is an interesting name for an organization. It uses a 30-meter antenna to capture the ranges in the 100 gigahertz to 370 gigahertz ranges. And the sister telescope to this is the array NOEMA, which was eventually added to the EHT array itself in 2018. And it was one of the other one is one of those arrays we will actually skip. There are two instruments in Hawaii for this array. One of them being the James Clerk Maxwell Telescope, which is based in Mauna Kea, Hawaii, on top of the big mountain. It was operated by the Joint Astronomy Center between 1987 and 2015 before it was sold or transitioned to the East Asian Observatory, which from a political standpoint is kind of an interesting one because it's an organization that has both China and Taiwan in the group, which, considering the hostilities between those countries, I found intriguing that they were able to get that to work. This is a 15 millimeter antenna, and it observes in the wavelengths of 0.4 to 1.4 millimeters. The other telescope that's based here in North America is the Large Millimeter Telescope, which is based in Volcan Sierra Negra in southern Mexico, which is very much closer to very south of Mexico. This is a co-national project which is operated jointly by the University of Massachusetts Amherst and the Mexican National Institute of Astrophysics, Optics, and Electronics. And this is the largest single element in the array with a 50 meter primary antenna, and is able to observe in wavelengths of 0.8 of just under 1 millimeter to up to 4 millimeters. And so you're seeing this pattern here of where all of these arrays are overlapping, which is partly a requirement of this. The second array that we have is based and of the two arrays that's based in Hawaii is a submillimeter array. This is itself not a single dish. It is an interferometry array on itself. So they are using the interferometry array to build a larger interferometry array, which is interesting in itself. This is operated by the Smithsonian Astrophysical Observatory and the Academic Seneca of Taiwan. And it is comprised of 8 6-meter dishes with antennas to capture, and its capture frequency ranges is in the 180 to 420 gigahertz range. Because taking advantage of the same mechanics that contribute to the EHT of using aperture synthesis, these individual elements allow it to act as a virtual 508-meter telescope just because of the positioning of the arrays and how they're spread out. The next object in this array, and I think I have one or two more, I'm hoping to finish these up really quickly, is the ALMA array, the Atacama Large 12-millimeter array. This is physically the single most powerful telescope in the array. And I think at one point I metric, I saw that if you took ALMA's data collection capabilities out of the EHT data, it would reduce the signal to noise ratio by like 45% or something huge. So ALMA itself is a very, very sensitive instrument. It is a joint partnership between 7 nations, the US and a combination of European and Asian nations. It's primarily operated as part of the European Southern Observatory Program. It utilizes 66 different independent antenna dishes with different sizes. There are 54 12-meter dishes and 12 7-meter dishes in the array. And this enables it to capture a very large swath of the spectrum going from 31 gigahertz all the way up to 1 terahertz, primarily driven by, if you recall those images earlier, the spacing in the array. So each of the individual arrays in ALMA is not actually fixed to the ground like the image kind of makes it look like it. Each of these arrays can be physically moved and repositioned across the plateau of which they're stationed on. So this allows it to tackle a very wide variety of targets, although I'm not quite sure how long it takes them to physically move each of these dishes because they are quite large and quite heavy. So that there's certainly a lot of considerations in the array when they receive proposals and how they sequence proposals in order to minimize the amount of moving that the array itself does. Because presumably, constantly moving these arrays does jostle some of the electronics surrounding them and may increase maintenance costs. This is the last element in the array. And the last element is the South Pole Telescope, at least for the original array, which is located at the geographic South Pole. It is not on Antarctica. It is literally at the South Pole. Its physical coordinates are like 89 degrees south, which is basically right on the geographic pole. It is operated by the University of Chicago, the National Science Foundation, and the Department of Energy. It itself is a single 10-meter antenna dish. Is just barely one of those that makes the cut over in terms of the frequency ranges necessary for the EHT to capture what it does. Interesting enough, the telescope currently has the world's most powerful operating cosmic microwave background camera. But this telescope's geographic position also presents challenges. I don't know if I get into it, but I think I talked about this later, but I'll go ahead and cut myself off on this. Is that when they were producing the images for M87 and Sagittarius A star, they actually photographed Sagittarius A star first. But at the time that they captured this data, it was winter in the southern hemisphere. And during winter, there are no flights that leave Antarctica for a 6-month period from April through October. And so even though they had this data, they couldn't get it out of Antarctica to bring it back to actually analyze it. And so just its geographic remoteness, it makes it very much a challenge to operate and collect data on from the overall way. Because with these observations, there's so much data collection involved that they don't send this over an internet It's just not physically possible to. It would take far too long. So it's actually faster just to take all the data, load it up on our hard drives, and ship the hard drives out because there's so much data involved. So with all these elements and these techniques, we go, well, what exactly have we looked at? What is the significance? So as we've mentioned, we photographed these two supermassive black holes, M87 star, Sagittarius A star. And we were specifically interested in these two images of a region just outside the event horizon, which is termed the last photon orbit, uh, which is a very specific region. It's not an actual single orbital line like you might see if you were looking at an orbital diagram of a satellite around Earth. It's like basically a region per se, where in this region, this is that sort of dividing line between if you're on the other side of the region, you fall into the black hole and you don't get out. So it's kind of that, it's not the event horizon's barrier itself. It's the point where if you go on it, you're at a point where you're a photon that's going to fall into the event horizon. You can't escape. You're on a one-way trip at that point. Interestingly enough, if you yourself are able to survive in this region of the last photon orbit, because of relativistic effects, if you spun yourself around fast enough, you could see your own face without a mirror, which I found was pretty cool. So with this last photon orbit, they wanted to specifically look and try to interpret this region, which is known as the black hole shadow, which is this characteristic that's found in a specific type of black hole known as a Kerr black hole. A Kerr black hole is it's not a static single object. It is a rotating electrically uncharged black hole. So the uncharged portion is really, I think, a semantic from a theorist point of view. In theory, there are constructs where you can make an electronically charged black hole. It does have an electric charge to it. I don't think there have been any detections of such an object in nature itself. So they're right now purely one of those theoretical things that physicists like to play around with. Well, for the uncharged black holes. But this rotation is what's one of the key components here, in that the rotation itself helps shape some of the characteristics that get imparted onto the accretion disk. So much like how the Earth itself bulges at the equator because of its own rotation, the same is true for a Kerr black hole, in that it is not a perfect sphere. The event horizon itself is distorted slightly into an ellipsoid bulge like the Earth. And so in this region of the last photon orbit, we're wanting to look at this area that's known as the black hole shadow, which sits in this weird, funky zone of, and I'll try to demonstrate this. There's an image coming up with this that might help with this a little more context. Is this area that sits kind of between the bright area of the accretion disk and the event horizon itself. It's sort of like this effect that's generated from this glowing black hole over the event horizon. But the reason this is important is from a physics standpoint, the properties that you can observe, and measure of the black hole shadow have very specific properties that allow you to extract more information about properties of the black hole. So by looking at this shadow and seeing and taking measurements of it, they can use this to basically as a sanity check on features of general relativity and say, like, are we actually seeing the things that general relativity tells us, or is there something more going on here that we haven't been able to detect before because of the extreme gravitational environment around black holes? What's important to note here, which is kind of deceptive on some of the images, is that because of gravitational lensing, this produces a magnifying effect of the shadow itself. And so when we look at this next image, we see that we have this single orbit here of this is both the event horizon in this outer white circle, which is the size of the event horizon. But we have these other dark areas that are outside of it. Like these are parts of the black hole shadow, and this area here is kind of the event horizon. And there's some overlap here near the bottom of the circle of part driven by gravitational lensing and the angle of the accretion disk from our point of perspective. Because my understanding is that the lower portion of the accretion disk is slightly tilted towards us, while this back half is slightly tilted away from us. So that we're looking kind of at like how Saturn's rings themselves are tilted, but we're still looking at this kind of from a top-down perspective, is what I understood. And so so this here is the last photon ring, which I think is at least at this point slightly different, because I did mention that I would expect it to be a little bit closer to the event horizon just from what I understood from reading the definition. So I'm not quite sure if this line is actually accurate. So when they were producing these results, because of the novelty, newness of these images and the techniques they were trying, they didn't actually process the data once. They processed it through 4 different techniques in order to just make sure that everything is a way to rule out, like, hey, there's bugs in our software that are producing results that we don't expect. So it is one of those ways that they can introduce a control mechanism into their results. They've since branched that out, so I think they settled around on a single technique afterwards once they found one that kind of worked best with their overall data. But since releasing the images of M87 and Sagittarius A star, it has gone on to image quite a few objects. We'll highlight, and I'll only show images of 2 of them, mostly focusing on supermassive black holes, blazars, and quasars. But they also revisited 2 portions of M87. So they're still looking at these supermassive black hole objects, although we aren't getting nearly the level of detail that we do with M87 and Sagittarius A star, just because we're looking at much smaller or much more distant supermassive black holes with these elements. So the 2 images that I actually found were slightly more interesting to go pull up for this comparison are on Centaurus A, which is a galaxy that we could see quite easily here coming in the upcoming spring. And they specifically wanted to image, as we could see, and image here and over here, there are actually a pair of jets coming out of the center of this galaxy. And so they turned the EHT array on this in order to look more at the properties of the relativistic jets of this black hole. And then Henry 3530 was quasar. Okay, yeah. And then over on the right, they were using it to image a quasar, which are very, very distant galaxies. So you don't get a lot of detail here overall. But they were able to detect quite a few things, and this was actually did actually get a chance to read the entirety of this paper in terms of exactly what these individual labels mean. I believe they're different elements of carbon or oxygen, but I could be mistaken. Oh, that's it for this. That was a lot of an information dump. So, questions, comments. I have literally 9 slides worth of references to make this presentation, so there was a lot here. Tom, I saw you come off mute, but I didn't hear your question. If you said
Well, I
anything,
haven't. I didn't ask yet, but I was just trying to think of how to ask. Um, Early in the presentation, you mentioned that maybe the light that we see from the accretion disk is not necessarily from the friction of the mass. Is it something else, something relativistic or something?
it's what I understood it as, and I'm not quite sure what EHT added onto this, because is that it has to do with how the mass changes speeds as it falls into the accretion disk. And so similar to how like you get when you do a lot of extreme braking on a car, your brakes heat up. It's
Sure.
similar to that same, it's fundamentally similar to that same effect of like the matter itself is braking as it falls into this black hole rather than speeding up, which is weird because the accretion disk itself is traveling at relativistic speeds. But it, from what I said, it's basically kind of like that.
Yeah, still kind of sounds like friction to me, though. But
Well, it's
yeah,
what misleading there is it's the mechanics that give rise to the friction is what they're what they were trying to answer.
gotcha. Okay.
Not necessarily like, hey, what is it, friction or is it something else? It's really about like what causes the friction, because it couldn't be from simulations. They're like, this can't be friction due to the atoms rubbing against each other, because I mentioned the accretion disk itself is apparently very diffuse. So some
Mhm.
other mechanism creates the friction.
Oh, it's diffuse. I would have kind of thought it was fairly
That's what
compressed.
I was surprised too when I
Yeah.
read that. I was like, it's diffuse, really?
Hmm.
But that's apparently the case. I don't know how diffuse is, because diffuse is one of those like really relative terms, and like you could say like, well, a star is diffuse compared to this other star, but they're still star densities. So in terms of like where that fits on the diffuse scale, I didn't really quantify.
Yeah, the only other thing I could think of is if there's some sort of relativistic thing like mass turning into energy, E equals mc squared thing or something. That's the only other thing I can think of where you would get, radiation or, some sort of indication of energy coming out of there. But I don't know what. So,
It's not an EMC sort of principle here,
okay.
for
Yeah.
that.
Okay.
I mean, it kind of is, but not in like the pure like, hey, this atom of dust turned into pure energy sort of thing. It's really more about like it's more a slightly more appropriate analogy would be sort of like the conservation of momentum effect, essentially. In terms of like, you're converting your momentum into, X-ray, gamma rays, and other forms of light in order to like keep the conservation of energy and the conservation of momentum. Not
Oh, interesting.
Probably not fully accurate. I'm
No, it's
throwing things in there that probably a physicist would yell at me. It's like, no, you're wrong. But that's kind of the way I would like to think about it. Is
yeah,
because
okay. Well, that's an interesting uh, thing to look into. I'll see what AI has to say about it. Yeah, thanks, Connor.
And Connor, not really a question for me. I put a comment as well. I thought this could easily become a very complicated topic and very confusing topic, but I thought you did a really nice job of presenting it so that I felt like I could follow most of it. And you actually gave me a really good like conversation starter now with the last photon orbit. I think
Yeah.
that could be a great icebreaker. Guess what? Did you know you can see your own face somewhere? We tell you about it.
you can see your own face without a mirror or a reflecting
Right.
surface.
Yeah. Yeah. So, nice job with the presentation.
Thank you.
Yeah, definitely. I have to agree with that too, Connor. You usually do a very good job of explaining what really are pretty complicated topics. On the subject of that last photon, that got me thinking also of, gee, what exactly is the definition of the event horizon? And last photon sort of does make sense. Once you've gone past that, that
So
is the event
the
horizon. Yeah.
the last photon orbit is not the event horizon. It's basically an orbital position outside the event horizon itself.
Mhm. Yeah, and one of your slides mentioned that, and what I was trying to understand is it kind of sounded like the black hole shadow uh, is well, I guess I think it said that the black hole shadow is that region outside of the last photon orbit.
It's like I really struggled to find a good definition of exactly what the black hole shadow is functionally formed by.
Hmm.
And it's like I could have been like, "Hey, ChatGPT, tell me what this is," but I didn't really have a way to actually verify if AI would have told me a right result in the first place. And I didn't want to put anything here where I myself could not go to something and look at the explanation and say, I understand this and this is correct. So
Well,
it's the way
the astronomers probably don't agree on it either. So,
I'm pretty sure they do. It's just it's one of those things where I haven't found a concise, digestible explanation for what it is that I could put in here that made sense to me.
yeah. Well, one thought that occurred to me when I read that was, okay, the very last photon that's orbiting, would we even be able to see it because it's about to fall in? So,
That's what I was kind of confused at too when I went back and looked at that image where somebody over so go back here. Here. This one. So back on this image itself here, where it's like they actually said, here's this last photon ring or this last photon orbit, which you can clearly see there's elements of the event horizon that are on both sides of it. So that's why it's kind of like confusing to me is like, what if what I was reading as definitions of what this was and where this ring itself was placed are the same thing,
mhm,
or if I
yeah,
or if I myself misunderstood what the article communicating on me, which is entirely possible as something with black holes. They're complicated objects.
absolutely.
Okay, I'm gonna go ahead and call it a night here, and go ahead and stop this recording when I figure out where Zoom put that button because it changes.